none of those things. For the first time, astronomers have strong evidence for a galaxy not having a significant amount of dark matter. Most astronomers currently believe that dark matter plays a fundamental role in our universe and the formation of galaxies. This is because galaxies seem to have a lot more mass than what we can account for based on just the stars we see. How much mass is in a system is determined by measuring the speed at which galaxies rotate or individual stars in a galaxy move. Without the gravity from that mass, a galaxy would fly apart if everything in it is moving as quickly as we observe it moving. Decades of research have led astronomers to the extraordinary conclusion that 85% of the mass in our universe is invisible in all wavelengths of radiation, and that it's composed of matter that does not contain protons or neutrons or any type of particle we've detected before, and that this invisible material is all around us, passing through us without interacting with regular matter except by gravity. For some, that's a tough pill to swallow, and a minority of astronomers wonder if maybe we just don't completely understand how gravity works. If that were the case, and it was an inherent property of gravity that causes galaxies to move the way they do, then we could expect all galaxies to behave the same way. In other words, they would all seem to have about the same portion of dark matter. But with the galaxy in this Hubble image, astronomers looked at the velocities of 10 globular clusters in the galaxy, each a spherical collection of hundreds of thousands of stars, and calculated that their movements can be accounted for entirely by the mass of the visible material in this system. That means this galaxy has little to no dark matter. Strangely, this absence of dark matter actually provides evidence that dark matter is real. It shows that dark matter isn't always coupled with regular matter, that it's something separate. You can have regular matter without dark matter. This galaxy is really weird even beyond the dark matter thing. You may have noticed you can see straight through it. That's because this galaxy is what's called an ultra-diffuse galaxy, which, as the name implies, is extremely low density. This galaxy is about the same volume as our own Milky Way galaxy, but only has about 0.5% the amount of stars. Though astronomers have known about ultra-diffuse galaxies since the early 1980s, they can be difficult to find since they're so faint. A team of astronomers is using an array of telephoto lenses called Dragonfly to seek out these ghostly-looking objects. They obtained observations from Dragonfly, the Sloan Digital Sky Survey, the Gemini Observatory, and the Keck Observatory, then requested time on the Hubble Space Telescope to take a closer look at this unusual galaxy. Having images and data from multiple sources allowed the team to determine that this galaxy does not have a significant amount of dark matter. This was definitely surprising to find. No other galaxies so far have appeared to be so lacking in dark matter. In fact, other ultra-diffuse galaxies seem to have an overabundance of dark matter. The same team who studied this galaxy discovered a different ultra-diffuse galaxy in 2016 that they calculated was 99.9% dark matter. Yet another weird thing about this galaxy, the globular clusters used to measure the galaxy's rotation are way brighter than normal globular clusters. The researchers have written a different paper that focuses on just these oddball collections of stars. So this is a very strange galaxy in several ways. Astronomers will be looking at Hubble observations of other ultra-diffuse galaxies to see if there are any other examples of galaxies with unusually low or high amounts of dark matter. With more samples, astronomers will be able to better understand the nature of dark matter, the formation and evolution of galaxies, and the overall structure of our universe.
So to set the context, though, I want to start by reminding you of a few basic facts about the universe that I think everyone should know. So the first fact is that the universe is very old. Does anyone know how old the universe is? 13.7. 13.7 billion. Good. All right, this is a good audience. Yes. You've been reading ahead, or it's older than Bernie Sanders, either way. That's it for the political jokes for the night. So it's actually 13.8 billion years. It's gotten older. So how do we know it's old? Well, there are a number of things. It contains old things in it besides Bernie Sanders. The Earth, we know, is about 4.5 billion years old. The Sun, about 5 billion years. The oldest stars in our galaxy, about 13 billion years. And most recently, observations of the cosmic microwave background, that we'll talk a little bit about later, have pinned it down to this 13.8 billion years. So this is just an example of some of the oldest stars in our galaxy. This is a globular star cluster, Omega Centaurus, an image taken by the dark energy camera that I'll be talking about later, of stars that are about 13 billion years old. Second basic fact about the universe, it's very big. I'm not going to ask how big it is, because it's really big. So the most distant objects we can see are about this many miles away. That's a lot of zeros. I think this is 100 zeta miles if you look it up. And of course, when we get to such large distances, miles are not a very good unit of distance because it's just too many zeros to keep track of. So instead, we use the fact that light travels very quickly, 186,000 miles a second. So in 1 year, light travels 6 trillion miles. So that defines a unit of distance, a light year. And so this many miles, that many zeros up there, it corresponds to about 30 billion light years. So that's the most distant things we see are about 30 billion light years away. And just to set the scale, the sun, our nearest star, is about 8 light minutes away. The nearest other stars near the sun are a few light years away. So the universe is very big. Third basic fact is the universe contains billions of galaxies in it. So if you travel to the southern hemisphere, you have the advantage, if any of you ever been down to the southern hemisphere, you go out on a dark night when it's clear, you can see galaxies with the naked eye. So just a little quiz. So this is a galaxy that we can actually see from the northern hemisphere too. Anybody know what this galaxy is? Milky Way, very good. All right, this is a very advanced audience, great. Does anybody know what that galaxy is? Oh, wow, great. Small Magellanic Cloud, that's right, and this is the Large Magellanic Cloud. These are two dwarf galaxy satellites of the Milky Way. You can only see them from the southern hemisphere, not from the north, so if you ever do go down south, I urge you to go out in a dark night and see if you can see them. They're quite spectacular. So these are examples of nearby galaxies, and the universe is filled with billions of these galaxies. This is a more typical galaxy, and they're typically about 60,000 light years across, contain tens of billions of stars, and they rotate like this galaxy, like our own Milky Way, rotates around its center on an average, takes about 200 million years to complete one rotation. This is also an image taken with our camera. So if we can bring the maybe lights down just a little bit, I want to show you a few examples of some pretty galaxies that we've taken pictures of with the dark energy camera. This is NGC 253. I'm sure you all knew that in the constellation Sculptor. And this is, of course, the familiar NGC 1566. Also, these galaxies are a few tens of millions of light years away. So galaxies, there are billions of them. They're all around the universe, but they don't exist in isolation. They live in and are shaped by a variety of environments and in proximity to other galaxies with which they occasionally interact. So sort of like my teenage daughters occasionally interact with me. Galaxies occasionally interact with others. Sometimes you find them in pairs or in groups or in clusters of tens to hundreds of thousands of galaxies. And those in themselves form part of a larger cosmic web of structure. We used to call these superclusters. So this is just one example here I pulled out. NGC 1672 is a nice large spiral galaxy in the foreground. But if you look down below here, you see a number of more distant, therefore they look smaller galaxies, in a group of galaxies. And this is sort of the first hint that these galaxies are not just randomly distributed throughout space. They cluster together. Here's NGC 1703 in the foreground, but if we look a little closer, and if you look on the right of that galaxy, again, you see a lot of these smaller yellowish galaxies. That's a more distant cluster of galaxies that happens to be behind this foreground cluster. So galaxies clump together into pairs, groups, and clusters of galaxies. This is a cluster of galaxies. Another image taken from the Dark Energy Survey. Again, all those yellowish galaxies are all in a relatively small volume of space, that being a few million light years across. and they cluster together. This is a very famous cluster of galaxies. This isn't an image from our survey, the Coma cluster of galaxies. Again, clusters are sort of the largest gravitationally bound systems we know of in the universe. Again, a few million light years across, and they contain about 1 quadrillion times the mass of the sun. So 1,000 trillion times the mass of our sun, typically. And again, that's composed of tens to thousands of galaxies. Now, Coma is an extremely important cluster of galaxies historically, because it was studied by this character, Fritz Zwicky, was an astronomer at Caltech in the first part of the 20th century. As you can probably tell from the image, Zwicky was quite a sort of irascible character. He was quite an eccentric personality, but he was also a pioneer of much of modern astronomy. He's one of the first to carry out a really major surveys of galaxies. He also is the discoverer of dark matter, as we'll talk about in a minute. Postulated neutron stars, did the first real quantitative studies of supernovae. And in the 1930s, Zwicky studied the motions of galaxies within that Coma cluster. He measured how fast the galaxies were moving with respect to us within the Coma cluster. And he found that those galaxies were moving remarkably fast, of order 1,000 kilometers per second relative to each other. And that was just simply too fast for them to remain confined by the gravitational field of the other galaxies in that cluster. So this was a puzzle. Why is the Coma cluster still there? Why haven't those galaxies all just streamed away from each other if they're moving so fast relative to each other? And so what Zwicky postulated was that the Coma cluster, in addition to the luminous galaxies we could see, that Coma was filled with dark matter. And that the gravity of that dark matter, the material that we can't see, must be the thing that's keeping the galaxies within the Coma cluster from flying off into extra cluster space. So he really was the first one to study this concept in detail, and concluded that clusters of galaxies are mostly made of dark matter. So an image like this, where we think we're looking at the cluster, we're really looking just at these galaxies that are kind of like sprinkles on this vast ice cream cone of dark matter. And we know the dark matter is there because it exerts this gravitational pull on the galaxies that we can see. All right, now we skip forward, and using Einstein's theory of relativity, so I'll remind you that Einstein reinvented our notion of how gravity works through the concept that gravity is not just a force between two massive bodies. Instead, massive bodies or any kind of energy curves space-time in its vicinity, and other bodies move in that curved space-time, and that's how gravity gets communicated. And using that concept then led Einstein to predict, and then the first real verification of his theory, was that light rays should get bent in gravitational fields due to this curvature of space-time. And so what this means is if I look at a distant galaxy behind a foreground concentration of mass, say a cluster of galaxies, then the shape of that distant galaxy will get distorted because the light rays coming to us get bent by the gravitational field of that cluster. So something that's intrinsically elliptical, looking at the lower right-hand portion, that's behind the cluster and near the line of sight to it, will get distorted into something that appears more like a banana or an arc. And this has now been observed many times in observations from the Hubble Space Telescope and from ground-based observatories. So what you're seeing here is an image from the Hubble Space Telescope of a cluster of galaxies. Those are the big, bright galaxies. But then you also see these faint, wispy, very elongated structures, these arcs. And those are images of distant galaxies behind the cluster. And the light has been bent passing through the cluster, and that leads to these very elongated apparent shapes. And you can use those images to actually reconstruct what the mass distribution of that cluster of galaxies is. And so these sharp peaks are where the galaxies in the cluster are. But then in addition to those sharp peaks, you see this overall sort of mountain of matter And that's all dark matter. That's a smoothly distributed dark matter in which these galaxies in that cluster are embedded. And so this is sort of direct confirmation of what Zwicky had found back in the 1930s. So skip forward now to the 1970s, and astronomers were studying the motions not only of galaxies within clusters, but of stars within individual galaxies. So this is the galaxy M33. It's a spiral galaxy similar to our Milky Way. It's rotating around its center, and you can measure the rotation speed of those stars around the center of the galaxy. This was done by Vera Rubin and collaborators in the 1970s. And what's shown here is a plot of the rotation speed in kilometers per second as a function of distance from the center of that galaxy M33. Now, what we expected is that as we move out from the center of the galaxy, the stars should be orbiting more and more slowly, because once you get far enough out, there's no more mass. It's just you've enclosed all the stars. And so you would expect the rotation versus distance to look something like that lower dashed line. And that's very much what the rotation curve of our solar system looks like, of planets moving around the sun. The farther the planets are away from the sun, the slower they're orbiting, because gravity is weaker. Instead, what Rubin and her collaborators found was that the rotation speed of stars around a galaxy keeps increasing and then sort of flattens out at a much higher value than would be expected just from the gravity of the stars contained within that galaxy. And this was, again, evidence that the bulk of the matter, of the mass in this galaxy was not contained in the stars that we see, but was in fact contained in some broader distribution of dark matter. And so, like Zwicky, Rubin found that the stars in a galaxy are moving faster than we can explain. The gravity of something that we can't see must be holding those stars in their orbits, and that's evidence for dark matter. And in fact, galaxies are mostly dark matter. The stars that we see in these galaxies are like, again, sprinkles on this much larger mass of dark matter ice cream. And again, we know it's there because of its gravitational effects. Again, skipping forward, just as we confirmed that fact in clusters of galaxies using gravitational lensing, we've also now confirmed the existence of dark matter in individual galaxies using the same gravitational lensing effect. So what you're seeing here are images of different galaxies, again from the Hubble Space Telescope. The yellowish blobs in the center is a foreground galaxy, and those bluish rings are actually the highly distorted images of another galaxy behind that foreground galaxy. And it's been distorted because the light from that distant galaxy was bent around by the mass of the foreground galaxy. And that very high lensing is again telling us about how much mass there is within the foreground galaxies, and it's much more than the mass contained in the stars. Here's another example of this. This is actually a system we found with the Sloan Digital Sky Survey and then followed up using the Hubble Space Telescope. So again, the yellowish blob in the center is a foreground galaxy. The blue ring around it is the highly distorted image of another galaxy that's behind it. Okay, and finally, we now do this on a kind of industrial scale where we can apply that same technique of lensing to study the shapes of galaxies behind thousands of foreground galaxies and do this in a kind of average statistical sense. This is called galaxy-galaxy lensing. And instead of probing the masses of individual galaxies, this lets us probe the sort of typical mass of average galaxies. And so we started using this technique back in the 1990s. And what we found, again, was that on average, luminous galaxies are embedded in these extended, what we call halos of dark matter. And so this was written up in the New York Times in late 1999. And apparently we were very surprised by this finding. Because that, to make it interesting for, there has to be some element of drama. I was actually much more interested in the article on prehistoric fashion. That was the other article in the newspaper that day. Okay, so we've now established that dark matter exists. It's the dominant form of mass in galaxies and in clusters of galaxies. So the natural question is, what is dark matter made of? Is it made, so what could it be made of? Well, there's the stuff we know about in the universe. It's atoms, which is made of electrons orbiting around a nucleus. The nucleus, more fundamentally, is made of protons and neutrons. The protons and neutrons, more fundamentally, are made of quarks. And so you might think, okay, maybe dark matter is made of some kind of atom that just, for whatever reason, is not shining light or emitting or interacting with light in some way. So could dark matter be made of atoms, something that's very dark? And so in early times, people thought, okay, maybe there could be very faint stars that we just too faint to see, maybe planets that aren't illuminated by a nearby star, maybe some kind of dirty rocks. And so astronomers searched for these, but we gradually concluded that there simply aren't enough atoms in the universe to account for all of the dark matter that we infer in galaxies and clusters of galaxies. There's too much dark matter out there compared to the amount of atoms that we have added up in the universe that we've now measured very precisely. So dark matter must be made of something other than atoms, or more fundamentally quarks, the things we study here at Fermilab. And perhaps it's made of some new kind of elementary particle that we've never seen before, that isn't, the atoms aren't composed of. And so our name for this is a weakly interacting massive particle, or WIMP. And so a WIMP is basically some new kind of elementary particle. It might be, say, 10 to 100 times the mass of a proton, which is so weakly interacting that we don't see it. It doesn't shine. It doesn't interact with light. But it could interact via the weak interaction with ordinary kinds of ordinary atoms. And so there are experiments around the world, sited deep underground, filled with atoms, as you've seen here. And they're looking for these WIMP particles coming from the dark halo of our galaxy. And the notion is that occasionally one of these WIMPs would come in, knock into the nucleus in an atom in this detector, and impart some energy into that nucleus, a very tiny amount. But if you have a sensitive enough detector, you can detect that energy that's deposited. And so there are a number of experiments now going around the world. Fermilab has an active program in searching for these dark matter, these WIMPs, using these techniques. There are a variety of different techniques. They all involve people wearing funny hats. This is an interesting field. There have been some of these experiments have claimed to have seen dark matter particles. Others that we think are more sensitive have not yet seen them. So it's an interesting time. And these experiments are getting more and more sensitive. And there's a hope that in the next decade, perhaps, we may actually detect in a verifiable way these dark matter particles. Another possibility is that we may actually produce these dark matter particles. You've all heard of the Large Hadron Collider at CERN, our sister laboratory in Switzerland, where the Higgs boson was discovered in 2012. They're bashing protons together at very unprecedentedly high energies. And the hope is that perhaps in one of these collisions of protons, they may produce dark matter particles, WIMPs, that we could infer through their signatures in these colliders. A third possibility for detecting dark matter is that we may see WIMPs annihilating with each other. So our current theory suggests that if there are dark matter WIMPs, particles, there would also be antiparticles floating around in the halo of our galaxy. And whenever a WIMP particle and antiparticle come close together and collide, they would annihilate, giving off a burst of energy, which would lead to radiation, high energy radiation, say gamma rays, that we could see if we have a gamma ray observatory. So NASA has such a gamma ray observatory orbiting the Earth, the Fermi Gamma Ray Satellite. And Fermi has been looking for signs of these anti-WIMP annihilations, looking both at the center of our Milky Way galaxy, which is very dense, so there may be a lot of dark matter there, and also looking at some of these other dwarf neighboring galaxies to the Milky Way, which are also very dense and would be places to look for this kind of annihilation signal. So Fermi is in the process of looking for gamma rays coming from WIMP annihilation. Okay, continuing on with the context, setting the basic facts of our universe. The fourth fact is that the universe is expanding. And this is traced to the work of Edwin Hubble. Hubble was an astronomer in the first half of the last century. And we have to talk about him because he was a graduate of the University of Chicago. Both his undergraduate and graduate degrees were there. He also studied law. He was a boxer. He did track and field. He played basketball. In his spare time, he did astronomy. And Hubble did some really amazing feats in observational astronomy in the first part of the 20th century. He's the one who really proved that spiral nebulae, these wispy things, which we now call galaxies, he's the one who proved that they are actually galaxies outside of our own Milky Way. Before then, there had been great uncertainty whether these things, these nebulae, were actually clouds of stars within our own galaxy. And he discovered the expanding universe in the late 1920s and went on to make important catalogs of galaxies and sky surveys. So here's a picture of Hubble using the Palomar 48-inch telescope. So has anybody noticed anything odd about this photograph of Hubble using the telescope? Well, he's not looking through the telescope, he's looking through the viewfinder, but yes, exactly, the lights are on. So to do astronomy, the lights have to be off, it has to be dark. So, you know, I sort of have my doubts about, you know, how authentic all this stuff really is because, you know, he should have known to turn the lights off. Anyway, before that, Hubble had a quite stellar athletic career. So here's Hubble with the 1909 National Championship, before the NCAA, I think, National Championship basketball team, 1909. And here is actually Hubble's championship basketball on the space shuttle with the Hubble Space Telescope in the background. The final score of that championship game was University of Chicago 18, Indiana 12. I think it took them a while before Steph Curry hadn't been invented yet. They didn't have three-pointers back then, so nevertheless, Hubble really went on to a brilliant career in astronomy, and to celebrate his career, astronomer John Grunsfeld, also a Chicago graduate, brought his basketball up to on one of the missions where they refurbished the Hubble Space Telescope. Okay, so here's the expanding universe. As time goes on, everything in the universe is moving away from everything else. If you were to run this movie backward in time, eventually everything would be on top of everything else. 13.8 billion years ago, that's what we call the Big Bang. And I want to just stress a few key points about the expanding universe. One is we're really talking about the distance between galaxies increasing. We don't think our galaxy is expanding. We don't think this room is expanding. I'm expanding, but that's because I eat too much. Generally, within our galaxy, gravity is keeping things sort of stable. So it's really the distance between galaxies which is increasing with time. And again, to give you a sense of scale, a galaxy 100 million light years away is moving away from us at 2,000 miles per second. So the universe is kind of humming along. Again, this was really established by Hubble in the late 1920s. Now, there are a lot of misconceptions about the expanding universe. And often, many of these misconceptions are traced to the fact that this picture, while useful, we have to be cautious in interpreting it because we're looking at a lower dimensional universe from our three-dimensional perspective. So we don't think the universe has a center or an edge, at least not that we can see. It looks the same everywhere. It's homogeneous and isotropic. And the expansion is happening everywhere. It's not exploding into empty space. And so really that picture of an expanding balloon is somewhat misleading. It's probably better to think of, say, an infinite raisin bread. Think of the raisins as galaxies. You put enough yeast into it and put it into the oven, and it will start to expand, each raisin will move away from all of the other raisins. That's probably a better analogy for the expanding universe. Another point to make is that as the universe expands, like any gas, it gets less dense and it cools off. Therefore, if we run the movie backward in time toward the Big Bang, it becomes hotter and denser. So today, the universe is very cold. It's only 3 degrees above absolute zero and very diffuse. The density of the universe is very low. But in the early universe, it was much hotter and much denser. And so this is now our best picture of the early universe, the cosmic microwave background radiation. This is as seen from the Planck satellite. So this is an all-sky image of the temperature of the universe as it appears today, 3 degrees above absolute zero. So the red and blue splotches are regions where the temperature is slightly hotter and slightly colder than the average. And that slight is only 1 part in 100,000. So the universe, to first approximation, has the same temperature everywhere, but it has these slight differences in temperature from one place to the other. Now, this is really giving us a snapshot of what the universe looked like when it was only 380,000 years old. It's now 13.8 billion. So this is really a picture of the adolescent universe. And at that time, it had a temperature of a few thousand degrees. But since then, with the expansion of the universe, it has cooled to a temperature of just below 3 degrees above zero. So this is a picture of what the universe looks like today. This is a map of galaxies from an infrared survey done a number of years ago. Each of the little white squares there is the location of a galaxy. There's a few million galaxies in this picture. The blue is just, this is in funny coordinates, so the blue is actually infrared emission from our own galaxy. And again, what you see here is that the universe today is actually quite lumpy. It's not obvious what the contrast is here, but the lumpiness of the universe today is orders of magnitude larger than it was 380,000 years after the Big Bang. And so our picture is that as the universe has evolved, it started from nearly homogeneous conditions. The density of the universe was almost the same everywhere in space. Whoops. But then, over time, gravity acted on slight differences in the density between different locations in space. Regions that were denser than average accrued matter onto them. Regions that were less dense than average became more and more vacuous. And eventually, large-scale structures formed. This kind of web, this thing we call the cosmic web. So this is a computer simulation of the evolution of structure from nearly homogeneous initial conditions to a very inhomogeneous universe that we see today. And in this simulation, the only ingredients are gravity acting on particles and dark matter particles, for example, WIMPs. They didn't even bother to put in atoms in this simulation because they're a small minority compared to the dark matter. And this simulated universe looks remarkably like that lumpy universe of galaxies that we actually see today. So our picture of the history of the universe is that it started in a Big Bang 13.8 billion years ago, started expanding very rapidly. That's a period we call cosmic inflation. Once it had reached about 380,000 years after the Big Bang, that's when the photons, the radiation in the microwave background, started streaming away from the atoms. And that gives us this picture of the microwave background that we saw from Planck. And then over the succeeding billions of years, those small fluctuations in the temperature and density of the universe evolved by a gravity into the large-scale structures we see today: galaxies, stars, planets, and larger-scale structures. So that's the picture we have now of how the universe has evolved. So we know the universe is expanding. And it's natural to ask, is the expansion changing over time? So what do we expect? Well, again, gravity is the dominant force on large scales. And so we can do a simple thought experiment. We're sitting here on the Milky Way. We look at all these other galaxies, these billions of galaxies. They're all receding away from us due to the expansion of the universe. But our galaxy is tugging on each of those galaxies because of gravity. we're exerting a gravitational force on all those billions of galaxies moving away from us. And therefore, we would expect that if we observed any one of those galaxies next year, 10 years from now, 100 years from now, the speed with which it's moving away from us should reduce over time. It should be slowing down because we're pulling on that galaxy. And so that was the expectation through much of the 20th century, was that the expansion should be gradually slowing down over time. And Hubble and many of the people he taught and worked with and who followed him tried to measure that slowing down of the cosmic expansion and never could do it because it was, the measurements are very challenging to make. And then in the late 1990s, two teams of astronomers studying distant supernovae in fact found that the expansion was not slowing down. They both found evidence that it was in fact speeding up over time. And this was led to the Nobel Prize in Physics in 2011 for the leaders of those two teams. So I want to talk a little bit about this discovery and some of its implications. So this is a supernova. This is the kind of event those astronomers were looking at. So this is a nearby galaxy. In the lower left, you see what looks like a bright star. That's in fact a star in that galaxy which exploded. And about 3 weeks after it exploded, it became nearly as bright as all the other billions of stars in that galaxy. So supernovae are remarkable events. They go from being fainter than the sun to being brighter than a billion suns over the course of just a few weeks, and then they fade over the course of a few months. And this is a gallery of about 500 supernovae that we discovered in the mid-2000s using the Sloan Digital Sky Survey. And again, what you do is you look at, you make a big survey of the sky, you come back sometime later, you look at the same patches of the sky, and you see if there's anything new there. And each of these blue splotches is a new star. It's a supernova that wasn't there when we took the images of those galaxies a few weeks before these. We think, so these supernovae that we're looking at are a particular kind of supernova called a type 1a supernovae. And we have good evidence that type 1a supernovae are explosions of what we call white dwarf stars. These are very compact stars. Our sun will eventually, we think, become a white dwarf star once it's finished burning all of its nuclear fuel, and it will become very compact and dense. And if you have a white dwarf star near another star, and either accreting material from it because of gravity, or else orbiting another white dwarf star and eventually colliding with it, in both of those cases, the mass of the white dwarf will increase until it reaches the maximum mass, called the Chandrasekhar mass, about 1.4 times the mass of a sun, and then it will explode. It will undergo a thermonuclear explosion. And it's those explosions and the radiation from those explosions that lead to these supernovae events that we see. And so these two teams of astronomers in the late 1990s, what they could do, what they realized was that these supernovae, these type 1a supernova explosions, all had about the same brightness. When about 3 weeks after they exploded, they reached their peak brightness and then faded. And they had determined that all of these supernovae had the same intrinsic luminosity. So they were all like 100-watt light bulbs, obviously much brighter, but all 100 watts, not 80 or 120. And so this means that these particular kinds of supernovae are what we call standard candles. And if you know how bright something is, then you can determine how far away it is relative to other supernovae. And so what they were able to plot was essentially, we could tell how big the universe was when they were exploded. That's the redshift. We can tell that from the spectrum of light. And then they used the brightness of these supernovae to essentially tell how far away they were, or alternatively, how far in the past they had exploded. And what we had expected was something like this black line, that a supernova that went off when the universe was 2/3 its present size would have a particular brightness. But the points there are showing you that instead, a supernova that went off when the universe had a certain fraction of its current size was actually about 25% fainter than we expected. And that was the indication that the expansion of the universe is not slowing down due to gravity, but is in fact speeding up. And that's what led to the Nobel Prize discovery. So why is this a strange phenomenon? Why is this a mystery? Well, whenever you have any kind of object, every time you've taken any object and you've thrown it up and dropped it, whenever you throw up a ball, as soon as it leaves your hand, it's moving upward, but what's happening? It's slowing down due to gravity. It's attracted to the center of the Earth. As soon as it leaves my hand, it starts to slow down, and because I can't throw very hard, eventually it reaches some maximum height and then falls back down to Earth. And every time you've thrown a ball up, that's what's happened. And that's because gravity is attractive. But what the universe is doing, it's sort of like, imagine I throw this ball up, and initially it starts slowing down due to gravity, but then at some point, instead of continuing to slow down and eventually hitting a maximum point and falling back to Earth, instead it starts to speed up and rockets out of the atmosphere of the Earth into outer space. That's what the universe is doing. Safe to say we've never seen that in our everyday experience. But that's why the acceleration of the expansion, the speed up of cosmic expansion, is a mystery. It's because it confounds our understanding of gravity. So what could be causing this speed up of the expansion of the universe? And we basically think there are two possibilities. The first possibility is that the universe is filled with some kind of stuff that gives rise to a kind of repulsive gravity. Gravity is usually attractive in our everyday experience, in the solar system, in our galaxy, but perhaps when we're talking about things on cosmic scales, there is some additional stuff in the universe. It's not dark matter, it's not atoms, it must be something else, which has the property that it makes things repel from each other and therefore speed away from each other. We now call this dark energy. And we think that the universe is 70% dark energy. That's one possibility. The other is that maybe something strange is going on with gravity when we get to cosmic scales. Again, in the Earth, the solar system, our galaxy, gravity obeys Einstein's theory of general relativity. It's attractive force. But again, perhaps when we get to very large scales, gravity behaves in a different way, in such a way that things can accelerate away from each other. So that's the second logical possibility, is that there's something going wrong with our understanding of gravity. So we now have this picture that's been put together just over the last 10, 15 years, that 95% of the universe is dark, doesn't emit with a light or interact with light. So the stuff we see in our everyday world, stuff made of atoms or more fundamentally quarks, that's only 5% of the universe. So the stuff we're trying to figure out the nature of, primarily here at Fermilab and elsewhere, that's only 5% of the universe. The stuff that we know about, the laws of physics that we know of. We think 25% is this dark matter. It's not made of atoms. It's made perhaps of some new elementary particle. And that's the stuff that's holding galaxies and clusters of galaxies together, and is the engine by which galaxies, with gravity, by which structure forms in the universe. And then we think the dominant component of the universe, 70%, is this dark energy, this gravitationally repulsive stuff that's actually speeding up the expansion of the universe. Dark energy is not something we observe in our everyday life. It has no tangible effects, again, on terrestrial scales. It's much too dilute, too weak a force. So it would only come into play on cosmic scales. Let me skip over that. So one interesting thing is, I said that the universe today, we think, is about 70% dark energy. That's if you look on the right-hand column, about 20% dark matter, about 4 or 5% atomic ordinary matter. But if we go back in time, then those relative amounts of those different components will change. We think that as the universe expands, dark matter becomes more dilute. Ordinary matter becomes more dilute because as things get, as the distance between them gets bigger, the density, the mass per unit volume goes down. But that doesn't happen with dark energy. So since dark energy is dominating today, as the universe, we think that the density of dark energy hasn't changed very much from today to earlier times. And that means if I go back in time when the universe was denser, higher density of dark matter and ordinary matter, that means dark energy was relatively less important. So if I go back to a time 9.5 billion years after the Big Bang, the middle column there, then we think the universe was about 50% dark energy, 43% or so dark matter, 7% ordinary matter. And if I go even further back in time to just 1 billion years after the Big Bang, then we think dark energy was only 1%. Dark matter was the dominant component, 84%, ordinary matter about 15%. And this is important because remember I showed you that movie of structure forming by gravity. That only works in a universe where the bulk of the stuff is dark matter. Once dark energy takes over, becomes more dominant than dark matter, structure can no longer form because dark energy is this repulsive force pushing things away from each other, where gravity was the thing pulling them together. So we think that before a few billion years, the universe actually was slowing down due to the gravity of dark matter. And then maybe 7, 8, 9 billion years after the Big Bang, dark matter became sufficiently dilute that dark energy took over and caused the universe to speed up. So what is dark energy? Well, we don't know. We think it's a component with negative pressure, and that's what we need in general relativity to make something which would be gravitationally repulsive. But we really don't have a good fundamental understanding of what dark energy is. Our most conservative hypothesis is that it's the energy of empty space itself, the vacuum. So if I take if I took this bottle of water, poured all the water out of it, put a vacuum hose on it, evacuated all the air from it, shielded it from cosmic rays, there would be no particles left in it, no ordinary matter. I could shield it from dark matter, and it would be empty space. In classical physics, empty space would have no energy. But in quantum physics, empty space has energy due to Heisenberg's uncertainty principle. And it turns out that in quantum mechanics, the energy of the vacuum would have the right properties to be dark energy. It would have this gravitationally repulsive effect. So that's the most conservative hypothesis. Now, the only slight problem with that hypothesis is that if I calculate how much energy there is in the vacuum in this little bottle of water, it's infinity. And I'm pretty sure there's not an infinite amount of energy inside this bottle. So that means that our calculations are wrong. And this has, in fact, been a major embarrassment for theoretical physics for the last century. We just don't have an understanding of why the vacuum, the energy of empty space, is not infinity or much larger than we observe it to be. So it's still a fundamental mystery. There are other suggestions for what the dark energy could be. One popular idea is that perhaps the energy of the dark energy is associated with a much, much lighter cousin of the Higgs boson, a different kind of field permeating the universe. But those ideas are even much more speculative. And so I thought what I would do would be, when you don't have the answer to something, you ask Siri. So Siri, what do you think the nature of dark energy is?
I'm sorry. I'm afraid I can't answer that.
Yeah. Okay. Well, it was worth a shot. Okay. I think Apple should be working on this better, but okay. All right, so we don't know what dark energy is. Siri doesn't even know what dark energy is. Nevertheless, dark energy is important. Why is it important? Well, the nature of dark energy is going to determine the future evolution of the universe. It's already 70% of the universe. I said it was a smaller fraction in the past. That means in the future, dark energy is going to be an increasing fraction of the universe. So it's dominating now. It's going to dominate, we think, into the future. And so we need to understand its properties if we are to have any hope of determining what the future evolution of the universe is going to be. And one way to do that, to understand the nature of dark energy, is to make maps of the universe. They can give us clues to what dark energy is. And so that leads me into the project I've been working on with colleagues here and around the world for a number of years called the Dark Energy Survey. And our basic goal is to make a map of the universe to try to understand the history of the expansion of the universe and the history of this growth of the clumpiness of the universe in order to get at the properties of dark energy or whatever is causing the universe to speed up. And so what we've done is we've built a camera for a telescope in Chile, and we're now conducting 2 surveys of the universe, taking pictures, snapshots of eventually 300 million galaxies over about 1/8 of the sky. And we're also taking snapshots of certain smaller regions of the sky, which we go back to and point in the same direction roughly every week to discover more of these supernovae. The Nobel Prize work was based on observations of just a few tens of supernovae. In this project, we're going to have observations of thousands of supernovae and hundreds of millions of galaxies. So we started, the survey started in late August of 2013. We just finished our 3rd observing season. It's supported in the United States by the Department of Energy and the National Science Foundation. So this is your tax dollars at work, and we are trying to spend them wisely. We also have foreign and institutional partners who have contributed to the project. And we're using this map to try to understand the history of cosmic expansion and the growth of structure using 4 primary techniques. I don't have time to go into them in detail, but I'll just list them. One is to study these clusters of galaxies and to actually take a census of clusters, count how many of them there are in a given volume of space. A second is this technique of gravitational lensing that I mentioned before. Look at the distortions of the shapes of distant galaxies as their light passes through the foreground distribution of dark matter. A third technique is just to measure the distribution of galaxies in space, what we call large-scale structure. And the fourth is the technique that led to the discovery of cosmic acceleration, these supernovae, but just to measure many more of them, measure them more precisely, and measure them to greater distances. So I think I'll skip, so I'll just mention one of these 4 techniques. This is weak gravitational lensing. So again, the idea here is we're measuring the shapes of very distant galaxies. The light from those galaxies is traveling towards us through this foreground distribution of dark matter, halos of dark matter associated with galaxies and clusters of galaxies. And as it travels through them, the light paths get bent. That's what Einstein's general relativity tells us. And that slight bending leads to slight distortions of the shapes of those galaxies. Before I showed you very pronounced distortions of the shapes of galaxies. That's what we call strong lensing. But that only happens to a minority of distant galaxies if they happen to be just near the line of sight to some foreground galaxy. All galaxies, all distant galaxies get weakly distorted, weakly lensed. And so we can measure this by using the shapes of these 200 million distant galaxies. And that will give us information on dark energy. So in order to do this project, we've built an international collaboration. We have 400 scientists from around the world. The project is led by a team here at Fermilab in the US, but we have collaborators in England and in Europe, Brazil, and Australia. And we use this telescope. This is the Blanco telescope on Cerro Tololo Inter-American Observatory. This is operated by the National Optical Astronomy Observatory. It's in the northern Andes Mountains of northern Chile. So inside, these are 3 different telescopes. The biggest one is that one with the silver dome in the middle. If you go inside that dome, this is what you see. So on the left, that big structure is the telescope itself. And what you see here is the mirror of the telescope. It has a diameter about 4 yards across, 4 meters. And so light comes in from the sky, bounces off of that mirror, and then goes up into our camera, which is this thing in the upper right. It actually goes through 5 different lenses which focus the light onto a big digital camera that's about this big around. So this is what the actual focal plane of the camera looked like. It's 570 million pixels. That doesn't sound like so much today. You know, your iPhone has 10 million pixels, but 10, 12 years ago, it sounded like more. And these are very special pixels. They're very sensitive to light. So when I take a picture of all of you with my camera, well, it has a flash. We don't have a flash. It cost $40 million, and they couldn't put a flash on it. But the point is, your iPhone takes great photos, but it needs light. Even this amount of light, it doesn't do so well in. But the universe is dark, right? 95% of it is dark. We're looking at these very distant, faint galaxies. We get very few photons in the minute and a half that we open our shutter. Very few photons per distant galaxy. And so these pixels have to be extremely sensitive. So we operate them at very low temperature, and they have very low noise compared to your digital cameras. And so this is a very finely tuned instrument. It was built here at Fermilab and installed on the telescope in 2012. And in fact, so on the right is a picture of the camera installed at the top end of the telescope. And you see at the top end of the telescope has those white rings. And before we took the camera down to Chile, you know, it's a remote mountaintop. We knew this would be a complex operation to install it. They hadn't actually removed the top end of the telescope in many decades. And so here at Fermilab, we decided to build a replica of the top end of the telescope. We call it a telescope simulator. So these white rings here have the same diameter as the rings at the top end of the telescope. But this big telescope simulator was out in one of the laboratories here on site, just a couple of miles away. And so we were able to put the camera together here, mounted on this telescope simulator, understand how to mount it and how it would work under various orientations. And that proved enormously beneficial when we went down to Chile to install it. It has, as I mentioned, 5 lenses. On the upper right is the biggest of the 5 lenses. It's nearly a meter across, so quite large optics, very precisely shaped. And then once the light goes through those 5 lenses, before it hits the digital camera focal plane itself, it goes through a filter. And we operate with 5 different filters at different times that let in either blue light or sort of mid-range optical light or near-infrared light. And these are very large optical filters, some of the largest ever built for astronomy. And the remarkable story here is that these filters, they are very difficult to manufacture, and they were made by this company in Japan just a few months after the tsunami of 2011 devastated the country. So a remarkable feat. So this is what an actual raw image from the camera looks like. So you know when you if you have a nice digital SLR, those different formats, JPEG, whatever, RAW. So we only use the RAW mode here. We don't use other modes in the camera. And so this is what a raw image looks like. And so each of these is a charge coupled device detector, 2,000 by 4,000 pixels. And we mosaic them together to make the focal plane. And so you can see galaxies, stars in our own galaxy, various sorts of artifacts. So a lot of work goes into cleaning those images of artifacts so that we can use them for astronomy. So this is one of the first images we took on the night of September 12th, 2012. Of a nearby cluster of galaxies, the Fornax cluster. And you can see these little blackened areas. Those are the divisions between those different charge-coupled device detectors in the focal plane. If I just zoom in on one of those CCDs and blow it up, This shows you one of the most prominent galaxies in the Fornax cluster, NGC 1365. Beautiful spiral galaxy. So this camera has one of the features that enables us to make this very large survey is that it covers a very wide field of view on the sky. It's 3 square degrees on the sky. So to give you a sense of scale, if we were to point it at the full moon, we could completely encapsulate the full moon. Whereas the Hubble Space Telescope, its cameras just cover a very small portion of the sky in any one picture. So it's a very wide field camera, which is what we want to be able to make a map over a very large swath of the universe. So each year, for about 5 months of the year, we just take snapshots around the sky, about 20,000 of them each year. So this is another example of one of the images we taken, NGC 1512, so it's about 38 million light years away. So this is a relatively nearby galaxy. Most of the things we're interested in studying for dark energy are these very faint, much more distant galaxies that are billions of light years away. Here's another example. I don't remember the phone number of this galaxy. Here's a cluster of galaxies. So you see a number of sort of galaxies of a similar color in a relatively small volume of space. Here's a number of what look like interacting galaxies. And to give you a sense of scale, this image, which is just from a portion of one of the images, contains about 50,000 galaxies in it. And so that's what we need in order to be able to make a map of hundreds of millions of galaxies over time. If I just blow that one up, and then you zoom in, you see there's a distant cluster of galaxies. So these are the kinds of things we're counting in order to probe cosmic acceleration and dark energy. We've also discovered a number of strong lensing systems. So these are, again, distant galaxies that are highly distorted because the light from them has passed by a foreground galaxy or cluster of galaxies and led to this strong distortion of the images. This is an actual map of dark matter in a cluster of galaxies similar to the one I showed you before, again using this weak lensing technique. So the image is an image of the cluster of galaxies. So you see these galaxies here are all in this foreground cluster. The colored contours are actually showing you the mass distribution of that cluster inferred from this gravitational lensing technique. So the red contours indicate a high density of mass. The bluer is a lower density. So we're using this technique to, again, map out the dark matter in these systems. The other thing I mentioned, we're also using this survey to find supernovae. And so here's one example. If I take, so again, this is that picture of the Fornax cluster. I'll zoom in on one particular CCD and blow it up, and then focus on the lower portion of that CCD and blow it up, focus it on this one particular galaxy. And then if I flip back and forth between two pictures of that galaxy taken a few weeks apart, then you see something has appeared. And that's a new supernova that we discovered in October of 2013. And we've now discovered well over 1,000 of these supernovae. Supernovae can be hard to see. If you're sitting up front, you can probably see it. If you're sitting far away, it's harder to see. But fortunately, they come with these green arrows. That makes it much easier to find them. OK. So this is actually the geometry of our survey, the footprint of the survey on the sky. So this is a picture of the sky in celestial coordinates, the coordinate system defined by the rotating Earth. The plane of our galaxy, of the stars rotating our galaxy, is this dotted line. We want to stay away from that, because if we have to look through the plane of our galaxy, a lot of the light's going to be absorbed and scattered by gas and dust in our galaxy. So we want to look outside of the plane, away from the plane of our galaxy. So that tells us we want to focus in this region of the sky. And then we also want to see what we can see overhead from Chile at night. And that's this, so we focused in on this kind of purplish, reddish, pinkish region here. So this is a region that covers about 1/8 of the total sky. And what we're doing over the course of these 5 years is just taking many snapshots through each of those 5 filters over this whole area of sky and making deeper and deeper maps. The little yellow regions, those are where the supernova fields, those are the ones that we come back and we point in those directions roughly once a week to discover supernovae and measure their brightnesses. And then the data that we've mostly analyzed so far is in this green patch. This is data we took before we actually started the survey when we were kind of testing things out. We called that science verification. So this is now a map of the galaxies, of a couple of million galaxies from that greenish area over in the lower right. And again, you see this kind of filamentary structure of the galaxy distribution, showing you the large-scale cosmic web. Again, this region of the sky is only 3% of the area that we will eventually cover. This is actually a map of the dark matter in that same region of the sky using this weak gravitational lensing technique. And there's a nice correlation between where the dark matter is and where the galaxies are. That's not surprising. We think galaxies in the cosmic web mostly trace out where the dark matter is. But we can now actually make maps of it using this lensing technique. This is now a more recent map that we've made. This covers about 1,000 square degrees. This is from the first of our 5 seasons. And this is the data that we're now analyzing. So this is, again, showing you the distribution of a few tens of millions of galaxies over the sky. You see this frothy filamentary structure of the cosmic web. And compare that to the region we've already analyzed. It's a much larger data set that we now have to play with. One of the things we've done is, in addition to using this data to probe dark energy, we can also use it to probe dark matter. And so here is a map showing you, again, that pinkish footprint on the sky, now superimposed on a picture of the southern sky from the telescope. And the little red dots are nearby galaxies that we discovered just last year. These are galaxies that are in our own cosmic backyard. These are dwarf galaxies. They're ultra faint. Some of them may contain only 1,000 stars or so, compared to the billions of stars in a typical galaxy. And these are satellites of our own Milky Way galaxy, much like the large and small Magellanic Clouds are satellites of our Milky Way. But these are much, much smaller, much fainter, and so we simply haven't been able to discover them until we've made this map. So we discovered 17 of these nearby dwarf galaxies just last year. And as I said, these little faint galaxies have the advantage that they're relatively nearby to us, to the Milky Way, and they're very rich in dark matter. They contain very few stars, mostly dark matter. And so we're searching in these dwarf galaxies to try to see the signal of that annihilation of weakly interacting massive particles. So this is now a gamma ray image from the Fermi Gamma Ray satellite of one of those dwarf galaxies that we discovered last year. We don't see any significant excess of gamma rays coming from that galaxy, so that allows us to put constraints on the nature of dark matter. And finally, a couple of other sort of fun things that have come out of this, nothing to do with dark energy or dark matter. But when you make a large map of the sky, it turns out to be useful for a variety of other things that we hadn't even thought of when we designed and started the survey. Namely, we can use this, we think, to understand more about the nature of our own solar system, the very nearby universe. So in the upper left is showing you the inner solar system, the sun surrounded by the inner planets, then the asteroids, and then Jupiter. In the upper right, we're zooming out to see the outer solar system, including Uranus, Neptune, and Pluto, the former planet, which we now realize is just one of a very large number of objects that we call Kuiper Belt objects. And in the lower right, we have a zoom out even further. So the solar system is now all contained in here. And in red is the orbit of an interesting planet called Sedna that was discovered a number of years ago. And Sedna, we think, is sort of has to do with, and then if we go up even further, we get to where we think there's this vast cloud of stuff called the the Oort cloud. And so it turns out that there's actually many hundreds of thousands, not only of inner solar system asteroids, but these Kuiper belt objects, and more generally what we call trans-Neptunian objects, things outside the orbit of Neptune. And so here is a plot on the sky of the known trans-Neptunian objects on the sky, superimposed on the footprint of our survey. And then this is the orbits that they would trace out over a period of 5 years. And so basically this curve is just tracing out the plane of orbits of planets in the solar system around the sun. But you can see that a number of these things should be within the footprint of our survey, and we should be able to detect them because they move around over time within our survey. So if we take pictures over the course of 5 years over our footprint, we'll see some of these objects move around, and we'll be able to trace out these trans-Neptunian objects and learn more about the solar system. And in particular, these supernova fields are very good for that because we observe them roughly once a week. And so over the last few years, we've detected a number of these new trans-Neptunian objects by looking for things that move over the course of weeks or months through these fields over time. And so this is a listing of all the new trans-Neptunian objects we had discovered as of last year. There was a lot of excitement in the astronomy community a month or two ago because two astronomers postulated the existence of a new planet. You've probably heard about it, called Planet 9. This is a planet that would have about 10 times the mass of the Earth. And it's postulated because of the regularity of the orbits of a number of these trans-Neptunian objects, including a couple that were found with our camera. And we've been quite excited about this because if Planet 9 truly exists, we think there's a good chance, this is the likely orbit, the orbit of this object is constrained by actually studies of the Cassini satellite orbiting around Saturn. If there was any additional mass out there, it would show up as a perturbation of that orbit. And so the most likely range of orbit for this Planet 9 directly crosses our survey footprint. So we have people in our team now trying to use our data to see if we can see any trace of this possible hypothetical new planet. And finally, as Andre mentioned, there was a lot of excitement last month with the announcement of the discovery of gravitational waves. This is a sort of warping of space-time that was predicted by Einstein's theory of relativity 100 years ago. And basically, what they discovered was the signal, the chirp, due to two black holes, each 30 times the mass of the sun, orbiting each other and eventually spiraling in and merging. And that's a very violent event from the point of view of space-time. It sends out these ripples of space-time, which were observed by the LIGO experiment using these two huge detectors, one in Washington State, the other in Louisiana. This is quite exciting, and LIGO is going to turn on again later this year. And we realized that LIGO was going to be turning on last year, and so we formed a project using our camera and our survey such that when LIGO said gee, we think we maybe have seen something, we would go and point our camera in the direction of the sky where they thought it was coming from and see if we could see an optical light counterpart to these gravity waves. Now, the problem is that with only two detectors, one in Washington and one in Louisiana, they couldn't determine very precisely where on the sky these gravity waves were coming from. To triangulate, to really determine the direction precisely, you need 3 points of a triangle. They only had 2. And so they had a rather large uncertainty in where on the sky this was. And so within a couple of days, we pointed our camera at the most likely region of sky where LIGO said they thought they saw this event. And we were searching for an optical counterpart. We didn't see anything. That's not too surprising because if they're black holes merging together, it's unlikely that you would form something that would give off optical light. However, in the future, LIGO will be sensitive not only to black holes merging, but also to neutron stars merging. And we think there's a good chance that when neutron stars collide together, they would give off optical light. So we will hopefully continue this program in the future. It kind of piggybacks on the survey that we're carrying out and synergizes with it in a nice way. And so our hope is that in the next year, perhaps, we may be able to discover optical counterparts for gravitational wave events for the first time. This is a picture of the Orion Nebula. This was taken with the dark energy camera. It has nothing to do with cosmology, but I thought it was a pretty picture. And this also has nothing to do with cosmology. This is a comet. So when we're pointing, a computer tells us where to point the camera on any given time and any given night. Our computer doesn't know about comets, and so there just happened to be this quite bright Comet Lovejoy, that was passing through while we took the picture, and so it makes a nice, pretty picture. All right, to summarize, the universe is about 13.8 billion years old. It's about 95% dark, 25% dark matter, which holds galaxies and clusters together. There's going to be a quiz at the end. About 70% dark energy. It's filled with billions of galaxies and clusters of galaxies that are mostly dark matter. It's expanding from a Big Bang that we've known for quite a while. For the last 18 years or so, we've known that that expansion is actually speeding up. We don't know why, but it's likely due to this dark energy, which makes up 70% of the universe. And with the dark energy survey and other surveys that will follow onto it, we're embarked on this journey to address this mystery, to try to understand, learn more about the history of the expansion of the universe, and therefore hopefully learn more about the future evolution of the cosmos. Thank you.
We'll take questions, probably about 20 minutes.
Sure. So I think there are people interested in questions. There's two folks with microphones, so just raise your hand and they will find you.
Thank you. The question I have, in the pictures that you've been showing us from the dark energy camera, how long is the exposure when you're making those images?
Okay, good question. So how long is the exposure? So in 4 of the 5 filters, our exposures are 90 seconds long, so a minute and a half. In the very reddest of those filters, we expose for 45 seconds. So each time we expose, we open the shutter for 90 seconds, close it, move the telescope point in a different direction, open it for 90 seconds, close it. And so their individual exposures are 90 seconds. But as I said, over time, we come back and revisit each part of the survey field 10 times in each of the filters. So by the end of the survey, each part of the sky will be covered 900 seconds of equivalent exposure time. Yeah, and then we layer them on top of each other, called co-addition.
Over here. Thanks for the great talk. It seems like the total energy of the universe is increasing. If that's correct, what happened to the law of conservation of energy?
Good question. So that's true. If dark energy is the dominant stuff in the universe, as I said, when the universe expands, the density of dark energy isn't going down. So therefore, so the energy per unit volume isn't decreasing. If the volume is increasing, then the energy would be increasing. So what happened to the law of conservation of energy? It's not true. Sorry. And actually, we've known that for going back way. So in Einstein's theory of relativity, energy as a global quantity is not conserved.
Left-hand side here.
Yes, at the beginning of your talk, you said the farthest objects are 30 billion years, 30 billion light years away.
Yeah,
how
give
can
or
that
take.
be if the universe is only 13.8 billion years old?
Yeah, I knew I was going to get that question. Good question. So it really comes down to how do we measure distances? And the point is, So, we measure distances with rulers or tape measures or something, right? That clearly doesn't work when I'm talking about things very far away. And so there are different ways to measure distances. So depending on those different ways of measuring distance, I can use the brightness of an object, I can use the apparent sizes of objects, and those can give me slightly different answers. So the 30 billion years was using one particular measure of distance that doesn't mean that, that anything moves faster than the speed of light. It's just due to the fact that when I get to very large cosmic distance scales, it takes a long time to measure that distance. And so depending on how you define distance, you can get different answers. No, it's not inaccurate. It just means that when I get to cosmic distances, when I tell you the distance to something, I also need to tell you which distance I'm using. And as long as I tell you which distance I'm using, it's fine. Trust me.
Second row over here, Josh.
Over here. Here we go.
Yeah.
So the ratio between dark energy and just regular matter, did you actually get that by looking at the amount of matter that there is, figuring out how much energy you'd need to accelerate to match your observations, and then just do the energy equivalent of that, and then just take the ratio?
Yes, exactly.
You're kidding. We need to talk later.
That's it, exactly.
Over here.
What's the difference between dark matter and gravity?
What's the difference between dark matter and gravity? Okay, so gravity is a force. It's an interaction. So gravity is anytime you have mass or energy, it creates a gravitational field, which exerts a force on any other body moving in that gravitational field. So gravity is the thing that dark matter causes, if you like. Dark matter is just stuff. It's mass. It's something that has mass that is dark. Beyond that, we don't really know what it is, but it's not in itself a force. It is. So in elementary particle physics, we have the basic particles of nature, the quarks. Those are the stuff that all of matter that we see is made of. And then we have the interactions, the forces between them. And gravity, so we usually talk about the strong force, the weak force, the electromagnetic force, and then there's the gravitational force. And so basically our picture of how physics works is that it's elementary particles interacting via forces. So dark matter we think is likely to be a new elementary particle. Gravity is one of the forces through which they interact. Sorry, microphone?
It's back here. I can repeat. Yeah.
So the question is, does that mean that dark matter does not produce gravity? No, we think dark matter does produce gravity. Any form of mass or energy produces gravity. But it's just, it's not the same as gravity, which is what the previous question was.
Middle back up here.
How close is our closest galaxy neighbor?
How close is our nearest galaxy? Well, some of these very faint dwarf galaxies are only tens of thousands of light years away. The largest big galaxy to ours, the closest one comparable in size to the Milky Way, is Andromeda, and that's about 2 million light years away, give or take. Galaxies, the typical separation in space between large galaxies is a few million light years.
So if we were trying to send a deep space mission to the Andromeda galaxy and the universe is expanding at 3,000 miles per second.
Okay, good question.
Wouldn't that put like you keep cutting the distance in half every time and you never get there?
Yeah, well, first of all, it would take a really long time. I know there's some people who are happy to go to Mars and not come back, but that would, anyway. So, yeah, although actually, so with Andromeda, I can sort of give you an answer without actually answering, because, so I said all these galaxies are expanding, moving away from our galaxy, and that's true of almost all galaxies. It's true of all distant galaxies. Andromeda actually happens to be gravitationally bound into a pair of galaxies with the Milky Way. So actually Andromeda is approaching us, and we think that eventually Andromeda and the Milky Way will collide and merge together in some number of billions of years. So actually, if you wanted to just go to Andromeda, then you could just wait a few billion years. But it's true, if you wanted to go to other galaxies, then yes, you have to go fast because they're moving away from us. But you can move faster. They're not moving faster than the speed of light, so we think you can get to them.
Left-hand side over here.
What's your favorite part of studying dark energy?
My favorite part?
Yeah. Like, why do you study dark energy? Like, what got you started in it?
Oh, good question. Well, actually, what got me started studying dark energy was, by training, I'm actually, and most of my career has been as a theoretical astrophysicist. And there was sort of indications going back to the early to mid 1990s, before the supernova discovery, that things were not quite right. We already had sort of tentative evidence that this picture of a slowing down universe wasn't quite holding up. So it was sort of pre-evidence, if you like, for what we now know is acceleration of the expansion. And I had, in my earlier career, focused on, so I mentioned in one of the slides that we think there was actually a much earlier epoch of very rapid expansion called primordial inflation. So we think that a tiny fraction of a second after the Big Bang, the universe was also actually speeding up. And then eventually inflation ended and it went into a decelerating, a slowing down expansion until dark energy took over. So we think that this is actually at least the second time in cosmic history that the universe is speeding up. And I had worked earlier in my career on some hypothetical ideas for what could be causing that earlier epoch of cosmic speed up, inflation. And so with some colleagues here, we started thinking about, well, gee, what could that same kind of phenomenon, I mentioned this very light, super light cousin of the Higgs boson, could that be causing the current epoch of cosmic acceleration? So that's really how I got into this study. And then in the late 1990s, the discovery of the direct evidence for cosmic acceleration from the supernovae got me into thinking about, okay, how can we test this idea? How can we learn more about it? Theorizing is great. I love theorists. But there are certain times when you just need more data to really make progress in understanding something. And my judgment has been that in dark energy, we really need to do these kinds of surveys to point us in a particular direction of theory.
Okay. Thank you for sharing.
Third row here.
My question is related to your slide, which shows percentages of dark energy, dark matter, and normal matter over the course of 13.7 billion years. Now, that slide shows that originally there was 17% of regular matter. Now we have only about 5%.
Right.
How do you explain this reduction, or in the amount of regular matter, where it disappears?
Okay, so basically,
going to the faint.
So the universe is expanding, and as any kind of, if you have a gas that expands, right, it becomes less dense. The distance between particles of the gas is increasing in time, so the mass per unit volume of that gas is decreasing. The universe is expanding, and so the density of ordinary matter and of dark matter we think is going down. So that's not surprising, but what's surprising is that we don't think that's happening for dark energy. As we expand the universe, dark energy seems to have this strange property, at least according to Einstein's theory, that as you expand it, it doesn't become more dilute. And therefore, as I look at different epochs of cosmic history, the relative density of both ordinary matter, atomic matter, and dark matter relative to dark energy is decreasing. It's decreasing, they're both decreasing at the same rate.
But wait, for a moment, it looks like we are losing the atoms, from our,
Yeah, we're not losing them, they're just moving away from each other. They're still there, they're just farther away.
Well, so it's a density that's different, not the amount. So what are we measuring, density or the...
Yeah, so think of it as density. It's the amount per unit volume.
What's the difference, the mass versus the density?
Yeah.
Okay, all right, thank you.
Left-hand side of the center section over here. Yep.
When you look at the fact that the universe is expanding and accelerating, that to me would imply that observers in our local group 100 billion or trillions of light years from now will not be able to see the universe as we observe it. Should we not record something for them to see the beauty of it today? Because they're going to see a lot less of it.
That's true. So yeah, that's a good point. In 100 billion years, we think the only galaxies we'll see will be the galaxies that are in our local group. So these ultra-faint dwarf galaxies, the Magellanic Clouds, and well, Andromeda by then will have merged with the Milky Way, but it'll only be a handful of very local galaxies that are bound to our Milky Way Andromeda supergalaxy. All the other galaxies, the billions of galaxies that we see today, will have expanded beyond our horizon. And so not only will we not know that the universe is accelerating, we won't even know that it's expanding. So I agree, we need to not only record this for future generations, but this also adds a great urgency to these kinds of studies. We need to fund them now because we only have 100 billion years to answer the question. And it's a really hard question. So, it could take that long. So yes, thank you for bringing that up.
Fifth row center here.
So I wanted to go back to the relative density. Did you arrange the amount of dark energy to be approximately proportional to the size of the known universe at the various epochs?
No, so what was assumed there was just that the density, the energy per unit volume of dark energy wasn't changing. Now, we don't know that that's strictly speaking true. It could be changing a little bit. It could be decreasing a little bit. Could actually, in some bizarre theories, could actually be increasing a little bit. But in that particular case, we were just assuming that it was constant.
So that's the result of those numbers, but
yeah, that's right.
We don't have measurements to confirm
That's right.
that.
Yeah, we don't. I can't. Yeah. So yeah, I should be clear. When the universe was 1 billion years old, I can't tell you that it was precisely 1% dark energy and not 2 or a half.
Fourth row right over here.
This is to piggyback on a couple of earlier questions about dark matter and whether it exerts gravitational forces.
Okay.
I think you had, in one of the earlier slides, you had said that the model for a galaxy would indicate that the stars on the outer edge are moving slower than they, or should be moving slower than they actually are.
If there was no dark matter.
Right.
Mm-hmm.
And then the planetary bodies within our solar system, do they conform to
Yes.
the expected model?
Yes.
So is that an indication that the region of space that the solar system exists in
Mm-hmm.
is relatively devoid of dark matter?
Good question. Very good question. So the answer is no. That in the following sense. So it's true. When I calculate the orbits of planets around the sun, I never take into account dark matter. Why is that? It's not because we think that the local region, the solar system, is somehow deficient in dark matter. It's just that the density of dark matter in our galaxy, in our solar system, is much lower than the gravity of the dark matter, if you like, is much weaker than the gravitational force of the sun. And so the sun is by far the largest component of mass in the solar system. The amount of mass in dark matter in the solar system is tiny by comparison. So we just don't need to include it. We think it's there, but it's just a negligible increase in what's already there in the sun and the planets. So good question.
Over on the right here.
Can you comment on the theory of dark energy changing into dark matter and vice versa? And is there any evidence that you have found?
Yeah, so there are some models, some theoretical models, where they try to relate dark matter to dark energy, perhaps have them maybe transmute into each other in some way. We certainly, haven't been able to do any observations yet that provide evidence for or against that. I should have mentioned that we have no good theory, accepted consensus theory of what dark energy is. So that means we actually have thousands of theories of what it could be, and that's one of them. But we haven't been able to really test that.
Take a couple more in the back over here.
Whatever happened to modified Newtonian dynamics as an explanation for all these phenomena?
Yeah, good question. So, so back in the 1970s and 80s, when Vera Rubin was doing her work finding that galaxies were spinning faster than they should be, most astronomers said, okay, there must be this additional stuff. We call it dark matter. They remembered Zwicky's work from the 30s that had shown the same thing in clusters of galaxies. But on the other hand, some people say, well, gee, I can't see this stuff. Aren't you just making stuff up? It's like, epicycles to explain the orbits of planets. Could it instead be something going on with our understanding of gravity? And so there was a theory called modified Newtonian dynamics. An Israeli physicist, Mordecai Milgram, showed that if you modified, so in high school physics, if you've taken high school physics, you learn this famous Newton's second law, right? F equals ma. The force you apply on a body of mass m causes it to accelerate with an acceleration a. What Milgram showed is that perhaps at very low accelerations, F equals ma is wrong. It gets replaced by F equals m times some other function of the acceleration a. And he showed that if you make that function the correct form at very low accelerations, you would get those same rotation curves for galaxies that Vera Rubin and her colleagues had found. So this was called modified Newtonian dynamics. And I would say when the only evidence we had was rotation curves of a small number of galaxies in Zwicky's work on coma, then you would have said, okay, yeah, maybe it's dark matter, maybe it's modified Newtonian dynamics. What's happened in the decades since then is that we have a huge abundance of evidence all pointing to this same picture of 25% of the universe being dark matter. We have the gravitational lensing maps I showed you. We have clusters, merging clusters of galaxies where we clearly see that the mass is not where the gas in the clusters is. And we have the cosmic microwave background pointing to a universe that again has a spatial geometry that's spatially Euclidean, and so we need to have enough matter to make that up. And so that we now have a whole host, we have the whole picture of how galaxies form. That simulation I showed relied crucially on there being dark matter interacting via gravity. So we now have this whole ream of evidence from the microwave background, large-scale structure, gravitational lensing, plus many more studies of rotation curves of galaxies, clusters, all pointing to this picture of a universe that's 25% dark matter. And so I think just the modified Newtonian dynamics, it's sort of an interesting observational, sort of almost phenomenological law, if you like, that galaxies appear to obey, but it doesn't hold up as a sort of theory in itself any longer. I think the preponderance of evidence for dark matter is now overwhelming.
So we'll do two more, one over here. Yep.
You mentioned that there was epochs of expansion of the universe. Does that mean, do you have evidence that there was a period when of contraction, everything went back to the single point of origin leading to the Big Bang?
So our current picture is that the universe, since the Big Bang, has been expanding. It's been expanding at different rates. We think shortly after the Big Bang, it went through this accelerator expansion. Then the expansion slowed down for a while. and then a few billion later started speeding up again. That's where we are now. We don't have any, the picture of a contracting universe would be, perhaps before the Big Bang, there was some earlier period of contraction and then expansion. There's been a lot of theoretical speculation about that, but we don't have, as yet, any direct observational tests of that.
And the back left over here.
And can you touch on what you found at Triangulum 2?
The dwarf galaxies? Yes. Okay. Sorry?
The whipping around.
The whipping around.
Whipping around. And it said it had the highest proportion of dark matter.
Oh.
That was in a Mars astronomy, quantum gravity, I think.
I'm not sure exactly what you're referring to, but there are, I think you're talking about one of the dwarf galaxies, right? Yeah, so these dwarf galaxies, as I mentioned, have relatively few stars. They're mostly made of dark matter. We're still trying to, so we can discover those galaxies. We then need to follow them up with other sorts of observations to really study them in detail. We're starting to do that now with a number of these. And then the other thing we can do is to search for gamma rays from them to see if there's dark matter annihilating in their cores. I would say, so one thing I said, sort of in passing, was that so far we've seen no concrete evidence of dark matter annihilating in the cores of these galaxies. Other people analyzing the same data, well, so there are sort of fluctuations in a few of these galaxies where you see some gamma rays coming from them. We don't think that's strong evidence for dark matter annihilation. Other people get more excited about that kind of thing, though. I'm not sure if that's what you're referring to or not. But.
I think we have one more in the far back, if that's okay, Josh?
Yeah.
All right.
Thank you. Maybe it's good I'm asking the last question, perhaps because the last question, or the question I'm going to ask is to speculate on the end of the universe as a result of dark energy. This was not rehearsed. The professor will tell you that we're not working in concert. So what I understand is, or at least my understanding of it is, that eventually as gravity, dark energy, assuming it continues to do what it's been doing, pulls the universe further and further apart, gravity will have less and less of an impact on every body, including, I'm on shaky grounds here, including atomic nuclei. And so is that what the big rip is, if I've gotten that correct?
Yeah, okay. So it depends on the nature of dark energy. If dark energy is just the energy of the vacuum of empty space, then we think the future scenario is going to be what we were talking about earlier, that eventually all the other galaxies will just recede away from us. We'll end up with this universe of our galaxy, a few neighboring galaxies. Otherwise, the laws of physics will look pretty much the same. There is a possibility, I just briefly mentioned it before, sort of an alternative theory of dark energy, which is not that, so if the dark energy is the energy of the vacuum, then as the universe expands, the density, the energy per unit volume of dark energy isn't changing. The big rip is a hypothetical alternative model where actually as the universe expands, the energy per unit volume, the density of dark energy, actually increases with time. Now, if that happens, then not only is the universe speeding up, but the speeding up is speeding up. And eventually, in that case, this repulsive force will not just push all the other galaxies away, but it will eventually become the dominant force even on human and subatomic scales. And it will basically overwhelm all other forces and basically rip all particles, all atoms in the universe to shreds. So that's why they call it the Big Rip. So that would be quite a spectacular end to the universe. It would basically just everything would blow apart. Again, we don't think that'll happen for tens of billions of years.
So I see Orlando gave the mic to someone over here. Do you mind doing just one more?
Sure.
Okay.
You've been doing this survey for several years now.
Is there any preliminary results that you could mention?
Yeah, so I showed you some, sort of pictorially, some of the results. We don't yet have any preliminary results on dark energy, on the nature of dark